And it's my pleasure to introduce to you Dr. Peter Folger. He is at the Congressional Research Service. And as a policy person, do I have any policy cohorts in the room by chance besides Dr. Folger? Well, I will tell you that if you're in the field of public policy, the Congressional Research Service is sort of the beacon of quality, nonpartisan, comprehensive, holistic view of an issue. If you've got a colleague or a friend that's just being introduced to GIS, for example, this is a piece that Dr. Folger authored last year, Geospatial Information and Geographic Information Systems, an overview for Congress, and that's their audience. Congress is their audience, and so they're having to tell the story to people who have all kinds of different backgrounds, and it's just, if you're ever looking for any topic almost, you can go to the Congressional Research Service and they've probably written something on it, so that's just kind of another data point for you. But Dr. Folger is a specialist in energy and national resources policy at the CRS, that's the Congressional Research Service. He's been there since 2006. He also, one of the things that's kind of intriguing to me is that he dances that technology policy line, and it's, and I imagine some of you do it and you probably don't even know it, but it's hard. You've got to have that conversation with the technical community and with the policy community and help the different groups know why they're important to each other. It's not very easy, but he's been quite successful of it, according to his bio, which I know you have available, serving as a Congressional Science Fellow in Senator Domeninci's office. And apparently he's a gold digger too, gold and silver, which is really, really interesting. He received his bachelor's from Dartmouth, his master's from the University of Montana, and his PhD from the Colorado School of Mines, and it's my pleasure to introduce Dr. Folger at this time.
Thank you very much, Marlette. That was a very nice introduction, and it's a pleasure to be here. I want to thank Spatial Plexus 2012 in general, but particularly Danielle for inviting me. It's a pleasure to get outside the Beltway every now and then, and particularly to get to meet you all, kind of the practitioners here in GIS. I, like many other people who have spoken today, am not a GIS person. I'm a policy person now, and I was a geologist, and I did mine gold for a while. Not a gold digger in some other sense. I want to make that clear at the outset. But so it's great to be here to be able to talk to you about some of the arguably wicked problems that face Congress, and maybe brainstorm a bit about ways to make them less wicked. You got a little bit of introduction about CRS already from Marla. Let me give you a little bit more, because if you're like most Americans, you've never heard of Congressional Research Service. We're one of 3 legislative branch agencies. We work for the Congress. The other 2 are probably more familiar: the Government Accountability Office, or GAO, and the Congressional Budget Office, or CBO. When they do their work, when they produce reports, analyses, they're made available to the public, and we don't do that. We have one sole client, that's the Congress, and we work on a confidential basis. So even though Marlette had a copy of that report, it's actually not available to you via our website. It's available to you through your senator, congressperson, or on a multitude of public websites. Once we produce something, Congress, and we deliver it to our client, they can do whatever they want with it. Give it to the New York Times, give it to anybody. And most of our reports are available via other websites. But a note of caution there, we update them continually, and sometimes the versions you see online may not be the most up-to-date versions. And I know I have to update a companion to that report now that I've learned about the census issue that came up in the House, brought to my attention this morning. So what we do, our reports, our analyses, the memoranda we write, they're for specific clients, the staff and the members themselves. We basically do research, analysis, and answer questions on just about any topic that Congress may ask, and what they're interested in. And I mentioned that they can make them available to anybody else. We have about 400 analysts like me who have some specific knowledge in a field or a topic or several topics. Now, I happen to be a geologist, and I think it was through that association with maps, and I may have mentioned to my boss that I once probably sat at a workstation at the dot prompt era and turned on some piece of Esri software back in my grad student days. But now I work on federal geospatial policy issues, so that sort of explains why I'm here. But like many of my colleagues at CRS, I also have an interest in using geospatial analysis tools and techniques in our work to help Congress analyze the policy issues that they work on. And I think Congress is becoming more interested in these techniques as well. You might have heard, if you were in our session before lunch, Daniel mentioned there's a Senate GIS working group. It's a really self-started collection of about, I think, 40 offices in the Senate, maybe not that many, but around that, of staff members really who want to use geospatial techniques within the offices to help their bosses solve problems and tell stories as well, how they can relate that to their constituents. So of the 400 analysts like me, we have one geospatial technician, and we hired him in February. So we're a little bit short on the expertise in GIS, which is why I'm sort of interested in talking to you here. We're looking for help in many different ways, and maybe we can come up with some ideas. So that's part of my interest, and I want to describe kind of a small sample. I'll give you 3 sort of examples of problems that we've worked on, people in my group, and how they may be amenable to a geospatial analysis, and maybe you can have some ideas and suggestions that we could use. Lastly, my first disclaimer is I'm not a GIS person. My second one is that remarks today are my views only. They don't represent the views of the CRS, Library of Congress, or the US Congress. I want to thank Tom McDermott at the outset for talking about wicked problems and sort of giving the overview, so this shortens my talk somewhat. He had 6 characteristics of wicked problems. I pulled the 1973 paper, which I think might have been the original paper discussing wicked problems, maybe not, and that was based on the 1969 talk at the AAAS. They list 10 bullets, so I think that's progress. We've gone from 10 ways of describing wicked problems to 6, so you did a good job going over them this morning. They're just bullet points here. I also want to apologize at the outset for having a word slide. I thought I might be violating some GIS code of conduct by having word slides. There's only 2, maybe there's 3 in this whole talk. I've got more graphics later. But Tom, I think, went over these pretty well. I just want to comment on a couple here that maybe more, that sort of struck me. All these resonate to me when I think about problems that Congress deals with, which I think are essentially all wicked problems, except for the sort of more trivial matters like naming public buildings or locating post offices. Those aren't maybe necessarily wicked problems, or they could turn wicked, I suppose. The next to last one, the causes of wicked problems can be explained in numerous ways. That explains a lot. I mean, here's a problem, but one side of the aisle thinks the reason for it is one thing, and the other side thinks the other. Lower taxes, less spending, perfect example. Or it could even be between the Senate and the House. The Senate thinks something, the House thinks something else. And the last bullet, the planner, in this case, has no right to be wrong. I don't think you mentioned that. It was part of the original paper. It's sort of distinguishing these types of problems from those problems that lend themselves to a scientific analysis, where you can come up with multiple working hypotheses, you can test them out. If you're wrong, that's okay. But with wicked problems, you sort of implement the solution and you're stuck with it. And by having no right to be wrong, it's that whatever you implement is the solution. You can't just sort of go back and say, well, better luck next time. Okay, so I'll start in on my 3 problems. You saw the title of the talk. I'm a geologist, so I sort of describe these in terms of earth, wind, fire, and water. And the first problem I'm going to talk about, this is an issue I worked on with a colleague. This is my earth slide. The next slide is going to be the air and fire part. So the issue here, something I've worked on since I got to CRS in 2006, is reducing greenhouse gas emissions to the atmosphere with a goal of mitigating harmful climate change. So the strategy I'm going to talk about is called carbon capture and sequestration, which maybe some of you heard about, but it's CCS. Basically, it works like this. You capture CO2 emissions at their source. You then transport them through a pipeline and then inject it in the ground. That's carbon capture and sequestration. It's designed to remove large amounts of CO2 before they reach the atmosphere. So starting with the last step, because I'm a geologist, the earth part, this is where the CO2 can be stored. So the Department of Energy put together this continental, or this North America map, basically showing in the light colors geologic basins. These are basically the broad areas that are most amenable to storing large amounts of CO2. And I'll talk about how much CO2 people are thinking of storing. This is based on a GIS-based tool called NatCarb that the DOE has. It's pretty nice. I stole the graphic from their website. Now, according to the DOE, the U.S. has the capacity to store between 1.65 and 22.3 trillion metric tons of CO2 in these saline formations. That's a big number, maybe hard to grasp, but what that translates into is over 700 years worth of CO2 emissions from power plants in the US at the minimum scale, minimum side, that's the 1.65 trillion, or maybe 10,000 years if you store it, if we have that, the maximum potential for storage at current emission rates. So it's a big number, and it's a lot of time, and you know, some people would argue, well, that will solve a lot of our problem. Now this is the air and the fire part, earth, air, and fire. So this is also from the NatCarb site, and it shows the location of major stationary sources of CO2 in North America, in the US and parts of Canada. Electricity generation, fire part, produced over 2.2 billion metric tons of CO2 in 2010. It's about 40% of US total emissions. So it's a big number. And that's why CCS has had some attraction. It's a way to capture a large fraction of our emissions using one technique. The power plants are in blue here. Orange is cement plants, yellow ethanol plants, red petroleum or natural gas plants. That's much of the universe in terms of the stationary sources of CO2. Most of the rest comes out of car and mobile emissions, if you will. So there's the sources. I showed you the sinks, and DOE did the GIS work for me here, mashed these two together. And at this kind of scale, it's not that bad a matchup. You've got sources kind of sitting close to or near the sinks. So many experts think because of this that connecting the sources to the sinks is not really an issue, not really a wicked problem at all. So why am I bringing this up? Well, we got asked, a colleague of mine, Paul Parfamac, and I got sort of a typical question, well, how does this work at a smaller scale? You know, will there be complications for this thing, and this was years ago, going forward? So what we did is we picked out the easiest part of the CCS problem, not the capture part, which is expensive and technology driven, not the sequestration part, we inject it in the ground, you have issues of permitting there, but just the transportation part, the easy part, the pipes. And Paul's our pipeline guy. We already transport about CO2 through about 4,000 miles of pipeline in the US. There's nothing really new in the technology and engineering. The US has 500,000 miles of natural gas, petroleum, and hazardous liquids pipelines. So Congress, though, was considering what would be required for a kind of a nationwide deployment of CCS, and sort of divergent views on the requirements tend to create some considerable uncertainty and complicate what would the federal role be in this case in terms of cost, rights of way, legal jurisdiction. So Paul and I, he's not a GIS guy either, did a very basic analysis of what are the possible pipeline requirements in one region using a geospatial approach, sort of to the limits of our crude abilities, and with the help of Library of Congress Map Division. So what we did is just pick out a portion of the country here, western Pennsylvania, eastern Ohio. And this map shows, in the squares, 11 major coal-fired power plants. Each one emits about 9 million metric tons of CO2 per year. They're pretty big. And we're also showing here, we looked at, in the green is the underlying geologic formation called the Rose Run Formation. And that's a possible potential reservoir. And in the green and red bar on the left, we're denoting what's kind of the suitability of that reservoir. Its thickness, its continuity, its lack or presence of faults and fractures that could leak, how good a reservoir is this based on the literature. And sort of not in the green is the less suitable, the red is the more suitable, so it's not that suitable reservoir, but it sits right underneath these power plants. So we use this as one end of the spectrum, okay. So what we did basically was our thesis was basically infrastructure requirements and the policy implications related to CO2 pipelines might become clearer, okay, when considering what the actual pipelines would look like. So we assumed that all the CO2 in this case would be injected directly into the Rose Run. Then we calculated or assumed that each plant would require about a 25-mile diameter radius, non-overlapping radius for injection. And then we just calculated the shortest pipeline routes so they wouldn't overlap. And we came up with, using a Carnegie Mellon University model, that the maximum length of a pipeline in this scenario was 32 miles, not too bad. And the average length was 11 miles. So according to the model, the average cost for 11 miles of pipeline would be about $6 million, or 10 cents per ton of transported CO2. So this gave us sort of one end of the spectrum to look at. with all our caveats and assumptions about this. But suppose the Rose Run is not suitable. Okay, what would be available to these power plants? So an alternative, and probably the nearest alternative, is what's called the Mount Simon Formation, a big thick sandstone formation to the west in Ohio and Indiana and Michigan. So this would be the other end of the spectrum. What would it take to build pipelines over there to the Mount Simon? It's about 130 miles at minimum, up to 294 miles from the power plants, according to our modeling. And the cost would be now $70 million to $180 million per pipeline, averaging $150 million. And levelized cost would be about $2 per ton per mile. So the scenario is less favorable. Not necessarily the worst case, though, because even here you can see the best parts of the Mount Simon are to the west. So the pipelines might even be longer. We might have to route them differently. We picked the most linear route that we could, avoiding national parks and things like state parks and things like that. Still, I mean, this is a crude, very simplistic approach, yet what it did for us is sort of put out two ends of the spectrum. And it helped Congress sort of say, okay, here's a worst case, possible worst case, here's a possible best case, here's sort of a range of alternatives. All of a sudden, the problem is a little bit stickier. It's a little bit more wicked than maybe just we can put everything in the ground right where we started. It really started a conversation both within the Congress, among the committees of jurisdiction, and without. We got a lot of papers that sort of riffed off this, kind of putting in more detail what we started. And that was, in our view, a success, got the conversation started. So it helped us understand the wickedness of the problem, and that helped us convey more accurately kind of the level of complexity of the problem to Congress. Okay, so that was the one I was most familiar with. The second topic I'm going to talk about is sort of another fire and water topic, and the broad issue for Congress here is how to increase the use of non-fossil fuel energy sources. How about solar power? This is the work of a colleague of mine, Nicole Carter. So, as it may seem obvious, many counties and parts of states of the Southwest are premium locations for locating solar power. As you can imagine, the sun's shining there. And perhaps what should be equally obvious is in those counties and those states, these counties have constrained water supplies. So like I said, this isn't something I work on directly, but my colleague Nicole works on this type of problem as part of this sort of basket of issues called the energy-water nexus. What happens when you're trying to increase energy resources, preserve water resources, how are they related? That's her study. So what this map is from a National Renewable Energy Lab study, NREL study, that shows the projection for potential concentrated solar capacity that could be built by 2050. So it's a potential map based on a number of different factors. What's the potential for generating electricity from concentrated solar power? They calculate about 55 gigawatts, which is not small beans by any means. And why concentrated solar power? It's attractive because it has the potential for generating large amounts of power. It can be stored, which is key, right? Because it needs to be generated during the day, stored and distributed at night to meet nighttime demand. So that's what concentrated solar power is all about. But water supply is an issue for locating not only solar power, but any thermoelectric plant in the Southwest. So the policy question for the local, the state, federal decision makers is whether and how to promote CSP development in the face of competing water demands. Interesting, why is there concern about the CSP footprint? CSP facilities using wet cooling, using water versus dry cooling, can consume more water per unit electricity than traditional fossil fuel facilities. So it's a tough trade-off there. You want to use a source that's not generating CO2, but now you're up against water constraints. And they're just water impacts are just one of many factors. There's cost, there's climate, air pollution, land, ocean impacts, wildlife that have to be weighed and judged when you're trading these things off. Also, states are, as you know, responsible for most water planning, management, allocation decisions, and electricity siting decisions. So whether and how the feds should promote water conservation, efficiency, markets, and regional state planning and collaboration is a matter of debate. So the policy issue that seems ripe for a geospatial approach is how to evaluate the extent and location of potential water resource implications for CSP deployment given the significant uncertainty about the future rate and location of that deployment. That's maybe in a nutshell, at least that's what my colleague thinks. And this is where she pointed this out. She said, you know, this is where additional analysis using a geospatial approach, how CSP would deploy, how it might affect local water availability would really benefit both Congress and maybe the states and the local decision makers when they're trying to evaluate the consequences. So, for example, here's a potential source of information. The Electric Power Research Institute, or EPRI, developed what they're calling an index of susceptibility of U.S. counties to water supply constraints. So, trying to match these two things up. And so this was derived by combining information on the extent of development of available renewable water supply, groundwater use, endangered species, drought susceptibility, estimated growth in water use, and summer deficits in water supply. So in that previous slide, NREL did not consider water availability as a constraint on the CSP deployment. They just show what it would be like in 2050 without considering water. So it's this overlap that presents the policy issue for us, for Congress, and also for the state and the local folks. So, should the federal government promote electricity generation given local water constraints and demands? If so, how? What kinds of solar technologies are most appropriate? CSP is just one. We also have to take into consideration these model inputs are dynamic, and so when, where, and how much CSP is installed by 2050, and the technologies that are used are sensitive to those policies. So the policy choices add to the level of complexity and wickedness. Also, Nicole pointed out to me that states like Arizona and New Mexico, interestingly enough, produce more electricity than they consume, and they export the surplus electricity to adjoining states. So an interesting twist to the wicked problem here is that the higher the water consumed per kilowatt hour, the more the Southwest limited water resources may be virtually exported to other regions. So it's the virtual export of water that raises policy questions about this issue on water resources. And so you could even argue that the impacts of developing solar power in a few counties, the negative impacts on water resources, are tough, while the benefits of electricity generation get exported to other states. So this is sort of just an example of what we haven't done much with this, but it's an example of the type of problem we come up with. What's the problem with development? Why don't we just go to solar power? Well, here's why. It's not a simple, tame problem at this point, but hopefully with using these types of data and analysis, we can sort of tame it to some degree and help at least Congress get their arms around the dimensions of the problem. Now, I'll just shift now to my last example here, and this is just strictly the water, so we're done with the land and the fire and the air. This is a water topic, and basically, this comes from a colleague of mine, Betsy Cody, who in her portfolio at CRS, she covers all Western water issues, but I think 80% of her time is devoted to this issue, which is the Bay Delta, the San Francisco Bay Delta area. It's where the Sacramento River and the San Joaquin River come together into the San Francisco Bay. And what I'm showing on the right here is a GIS-based map that we actually put together. Jim Uzel, our GIS coordinator, the one guy, put this together based on some work we've done previously. But it is a GIS with several layers, and I'll talk about it in a little blow up in a few minutes here. But basically what I wanted to show is, in a very simplistic way, how the water flows in the Bay Delta. Some of you may be very familiar with this, some may not. But basically the blue shows the reservoirs where the water is collected. The water is released into the delta from the reservoirs, then pumped into the Central Valley, major agricultural region of the US, or to Southern California. And some of the water is used in the delta itself for ag, municipal use, industrial use, and fish and wildlife. So that, in a very simplistic way, that's how the water flows. Who controls the water? Here's where it starts to get really complicated, because there's a federal role, a state role, and a private role. The Central Valley Project, run by the Bureau of Reclamation, is the federal project here. There's a state water project, as per the name, and there's also people who have water rights to the use of the water, riparian water rights, which are more familiar to Eastern folks, people who basically have land on the banks of rivers, and the Western or appropriative water rights, which is first in use, or first in time, first in right, use it or lose it. That's the Western water law side. So you've got those different controls of the water, complicated flow system, and things get pretty wicked pretty fast. So, in fact, I would argue that the combination of the supply, the combination of the various types of demand, the federal water system, states, plus the possible effects of climate change on kind of the timing and the amount of snowpack in the Sierras, which is ultimately the reservoir in the wintertime. You could argue this is kind of the ultimate wicked water problem for the West. What I want to do, if I can here, is there, there we go. No, well, not working. I have a blow up. I'll show another slide later on. It's a bit of a blow up just to show some more of the details. But basically, in addition to the blue reservoirs you see there, the purple area, the yellow areas are where the users are located, different contractors to the different types of water supply. And then you can see there are lines on the map, some of which denote canals, conveyance systems. So what we're really just showing here are kind of the users, the source, and the conveyances in this part of for the Bay Delta. So that's how it works. What makes it complicated, in addition to those users, farmers and towns and industrial users, is the various regulations and laws that have been passed that add in different aspects, the environmental quality side, the water quality, the fish and wildlife. And I pulled out 3 bullets here, 3 different, if you will, controls, legislation or regulatory regulations that control that touch on that. First is the 95 Delta Water Quality Control Plan, which the state came up with to comply with the Clean Water Act. Basically, that amended the water rights previously in the Central Valley Project and the State Water Project. It required export limits. It limited the amount of water that could be exported and the timing. And also it set flow and water quality objectives for water supply and for fish and wildlife purposes. That's one. 92 Central Valley Project Improvement Act, it elevated fish and wildlife as official project purposes, I think for the first time. It mandated mitigation of some Central Valley Project damages to fish and wildlife resources, required a doubling of certain fish populations, and allocated a specific amount, 800,000 acre-feet of Central Valley Project water to fish and wildlife purposes. So now you have more demand, okay? The complexity and the wickedness of the problem goes up. And lastly, the Endangered Species Act. So where there's endangered or threatened species, that also has an influence on where the water goes to preserve those species. You may have heard of the Delta smelt. I don't know if you follow this, but it's not just one smelt, it's a whole species, but it is, I call it the Delta smelt. So that just adds the level of wickedness. Now you've got fish and wildlife, water quality, supply, and really, if you know, this wouldn't be a wicked problem if the amount of available water doubled or tripled in a year, and it was available exactly the right time in exactly the right place, right? But that's not going to happen. It might go the other way, as a matter of fact, if climate change, the impacts of climate change, as some of the models say, diminish the amount of snowpack in the Sierras and change the timing. So this is just the blow-up I was going to try to show you earlier. This focuses in on the bay itself. Now you can get a clearer picture of those regions of where the contractors are, and also the green down here is a wildlife management area. We put this together in a way as a snapshot, really, to sort of see the whole problem in one visual look, which is very helpful to members of Congress and staff and ourselves to sort of put it all together. And there's other layers to this model as well. But I also wanted to point out here another layer of complexity in addition to just kind of the physical infrastructure, and that is congressional districts and the representatives for those districts in Congress. Now, I count at least 19 congressional districts in this map alone, which means 19 representatives and 2 senators of the state have a direct interest, plus representatives to the north, where there's supply, and the users to the south. In fact, about 25 million people depend on water from this system. So it's a big deal. So this additional GIS layer here, the congressional district layer, I point out because even though members of Congress may not see this problem through geospatial goggles, which is what Daniel is calling this conference, they certainly do see them through their congressional district goggles. And so you have to factor in, we do at CRS, whenever we're working on a problem like this, or any problem really, how the member of Congress is looking through their congressional district lens at the problem. And they see things through that lens, the needs and desires of their constituents of any particular district are going to be evaluated, along with the physical infrastructure that we depict here. We try to keep that in mind when we're answering questions and doing analysis for Congress, is to keep that congressional district, state boundaries in mind. In fact, I'll finish on that sort of theme here. In that I'd say any problem we deal with that lends itself to a spatial analysis has to look at 3 additional GIS layers. I call this the congressional base layer. So I think all Congress sees its policy issues at some fundamental level as the boundaries of the United States, which I'm sort of depicting here. At some level, they all act as representatives of the United States, even though, of course, the president's the only truly elected leader of the entire country. So seeing the borders of the U.S., they sort of see things at that first level. Secondly, borders of the states. So here you have 2 senators, at least 100 members, 2 senators per state, see the world through their state boundaries. And in fact, in several states, as you know, Montana, I think the Dakotas, Vermont, there's only enough population for 1 representative. So there's 2 senators, but the 1 representative also sees issues through their state boundaries. Of course, it also means that states like Montana, Vermont, the Dakotas, Alaska, when they vote, they only have a block of 1 in the House of Representatives, whereas California has 52 representatives. So that makes a difference in how things get done often. But lastly, here's a map that shows the congressional districts themselves, and some are geographically large, some are small, in the state of Montana to some of the districts around New York and LA and the central, or the San Francisco that I just showed you. So again, just to sort of reiterate, my point here is that the perspective, when applying any type of geospatial analysis to issues that confront Congress, you got to bear in mind that their perspective is shaped by these 3 base layers, their own sets of goggles, the national boundaries, the state boundaries, and the congressional district boundaries, and sometimes all 3 together. I'm a geologist by background, so whenever I finish a talk, usually I put up a sunset or a nice picture of an outcrop, but now I'm in the social science sphere, so I'm giving you a word slide here. And this closing thought, I'd say this is probably disturbing to some people, but maybe the promise of job security to others. Thank you very much.